All right, now I'm very excited to introduce Alana Marzoev. Alana is the CEO and founder of ReadySet, which is a 2.5-year-old startup that is solving some really hard problems in the database and distributed systems world, which you're going to hear more about shortly. Prior to ReadySet, Alana was working on her PhD in the database and systems group at MIT. Prior to that, she also did some work at Microsoft Research in the cloud infrastructure group, and she also spent time at Berkeley's RISE lab, which is one of the best research labs in databases and distributed systems. ReadySet is also an Amplify investment, so we are very excited for her to be here today, and I'm excited for you all to hear more from Alana.
Hello, testing. Okay, I think we're good. Hey everyone, thank you for that lovely intro, Natalie. As you said, hi, I'm Alana Marzoev. I'm the co-founder and CEO of ReadySet, and today we're going to be talking about the first hardest problem in computer science. So you might be wondering, is there really an ordered list of hard problems in computer science? And if so, how did we come up with the specific ordering? Well, you see, this is just a reference to a very popular quote amidst tech circles, which is that there are only two hard things in computer science. The first is cache invalidation, and the second is naming things. And so in this talk, we're going to be talking a lot about caching and cache invalidation, but we're also going to go a little bit broader. I'm going to tell you more about database read performance in general, like what it is, why it matters, why in certain circumstances it's really hard to achieve good database read performance. And then I'm going to transition to talking through a few approaches that engineering teams take in practice today for scaling their data layers. And then finally, we're going to do a deep dive on caching. I'll explain why caching is hard, and I'll give you an overview of what we're building at ReadySet and how it can help alleviate some of the pain points around it. Cool, and in the context of this talk, I'm going to be really narrowing in on web applications in particular and how to scale them, but it's important to note that a lot of the ideas that we'll discuss are actually applicable to a really broad set of domains, so it's not just for web apps. Web apps just happen to be a really fantastic example of it. So without further ado, websites, they play a really big role in a lot of our personal and professional lives, and as end users of these applications, there's a few things that we expect. So the first thing is, like, as an end user, we want page load times to be very fast. As we're clicking around from page to page, we want new content to appear instantaneously. And in fact, there's a lot of research that shows that when this doesn't happen and page load latencies exceed past this threshold of roughly 100 milliseconds to time to see first content, then you see a spike in things like user churn, as end users were unlikely to return to the site because it's kind of a frustrating experience. The second desiderata is high availability. As an end user of these applications, I expect them to be available 24/7, 365 days of the year, and I expect page load times to be good on all of those days. It doesn't really matter to me if it's Black Friday, for example, or a popular internet day where there's potentially millions of other users also on the same site. I would still expect the same experience as any other day. And then finally, as an end user of these applications, we all generally expect real-time updates. To illustrate this point, consider if you're using a social network, for example. If one of your friends posts an update, you would expect to see that update within a few seconds, not hours. And that's generally true outside of the social context as well. In general, sites nowadays are very dynamic, and we expect the content to reflect kind of the state of the world rather than there being a really large time delay. And so in all of these contexts, SQL queries are almost always the bottleneck, because really what we're doing when we're issuing these web requests and loading pages is executing dozens or sometimes even hundreds of SQL queries behind the scenes. And nowadays, it's really popular to use database tools like ORMs, which are unfortunately notorious for generating both inefficient queries as well as really large numbers of them. So every time we're clicking from page to page, we're generating dozens or hundreds of SQL queries. And then of course, every user that's doing this, and there could be thousands, hundreds of thousands, millions, is doing the same thing. So at the end of the day, there's a lot of load, lots of queries that we're sending to the poor database behind the scenes. And it's important to note that when you start writing a new application, at least, typically you're going to go with a single server relational database. This is very much the status quo vanilla normal choice. Your data layer is not typically your initial focus. You just care about writing features, right? And there's this really nice quote that I love from the Box Engineering blog from Vovo Galchenko that I think really paints this picture nicely. And it says, The data access layer of $1 million idea starts out as just a single server relational database. You're not worried about scaling scaling issues. You have an application to write. However, if your $1 million idea ends up being worth even $100,000, you're likely going to find your database struggling to keep up with the scale. So that's the problem that we're contending with at the end of the day. And I'm going to argue that achieving this, like scaling your data layer more generally, is a really non-trivial problem. Enterprises and startups all face it. Like pretty much everyone deals with this when dealing with any amount of like user traffic, really. And enterprises have the benefit of like being able to like dedicate entire like engineering organizations towards solving this exact problem. Startups, unfortunately, like aren't as lucky. Like typically the first time they run into some of these issues, like they will like end up having like an outage or really bad performance that could drive away a lot of their users at a critical point in their timeline. So in both cases, it's a hard problem, and it's worthwhile to point out that the problem is constantly evolving over time. Like as your business grows, like your needs change, like maybe you're hitting that next order of magnitude of user traffic, or you're introducing a new product line entirely. But this isn't like a one and done type of fix. Like this is a problem that you're continuously revisiting over time. And so in this talk, we're going to discuss just a handful of the approaches that engineering teams will take when solving this problem. And then I'll also walk you through Ready Set and like our take on SQL caching and kind of like our intentions to alleviate some of these pain points. Cool. Before I go into all of that, though, I wanted to take a moment to like take a step back and really take a look at like what I mean by database read performance with the intention of making this talk accessible to a broader set of audiences. So what is a database read, you might be asking? Pretty straightforward. Whenever I say read, I just mean SQL query. So think like SQL statement with a select clause that is returning data from your database. You can contrast that to writes, which are like inserts or updates that are actually changing the state of your database. Like reads don't change the state; they're just you're just returning results that to some question that you have essentially. And when I think about database read performance, there are two things that I care a lot about. The first is latencies, and the second is throughput, both like query latencies and query throughput, I should say. So for latencies, you can think of it as being like the amount of time it takes to run a single query. And so whenever I talk about page load times, like I want your minds to go immediately to latencies, because as we discussed, when you're loading a page, you're running a lot of SQL queries in the background, and their latencies are going to ultimately contribute to the overall page load times. The other thing that we care a lot about is query throughput. And you can think of query throughput as being like the number of queries you're running per time period. A really common one is like queries per second, for example. And whenever I talk about like volume, traffic of like queries or users, your mind should go directly to throughput. And they're pretty closely related. So oftentimes, like we like to think about like this like max throughput threshold for any given system. And there's like a plot that I included here. I know it's a little bit small for the people in person, but as you can see on this plot, like the x-axis is offered load and requests per second, so think throughput, and then the y-axis is 95th percentile latencies, so latencies, right? And you can see that for most of like the systems on this plot, as you continue to like gradually increase throughput, latencies will start to degrade up until a certain threshold where it's not just like a little minor degradation in latencies, but suddenly like, things spike up, so you can look at like the gray line and the green line. And at that point, like it's not worth continuing to try to send more queries to your system because it just falls over. Like all of the query latencies are like, a lot worse than they were previously, and you're not really doing yourself any favors. The system tends to fall over at that point, and that's what causes these types of like failures and outages at the end of the day. So, yeah. I also wanted to briefly talk about like generically like what causes bad database read performance. As I alluded to in the prior slide, high query volumes is one very common culprit, but there are a few others. So another is inefficient queries. So the idea of an inefficient query is like in general, you can write SQL queries in different ways while still like getting the same result set. And some of those ways might be a lot less efficient than others. And your database will generally try to help you with that, but there's still some hand optimization that you have to do at times. And so, inefficient queries just are fundamentally doing more work and they tend to be slower. Complex queries, on the other hand, are just like fundamentally encoding like more complex business logic. So if you like put aside any notion of efficiency, like sometimes like the questions that you ask of your data are just more complicated, which means that you have to do more work behind the scenes to compute the answers. And then finally, when you have large data sets, that just means like that the input to like whatever function you're running is larger. And again, you're doing more work. Typically, like if you have like the same queries, but one is run over like a much larger data set, it will be slower than the one that's run over a really tiny data set, for example. And in practice, it's really like when you have bad database read performance, it tends to be due to a combination of these factors rather than necessarily just one. And so you have to like root cause analysis this, figure out the one that's causing the problem, and then that would therefore would then inform which specific approach you might take to solving the problem. And again, like you're probably going to revisit this a lot over the course of like your application's lifecycle. Cool. So now I'm going to transition into talking about different approaches for scaling your data layer. So the first is query optimization. This one's pretty straightforward. We're coming back to this idea of inefficient queries. Like, again, like disclaimer, there has been decades of database like research that has gone into trying to make database like query optimizers really good. But unfortunately, it is still the case that if you like kind of understand how your database works and understand like the high level rules for like, what types of queries tend to be more efficient than others, then you will often get much better outcomes in terms of database read performance if you go back and like take a look at those queries, like see which ones are problematic and then hand optimize them. And if your queries are inefficient, then that could lead to better query latencies in those cases. But unfortunately, like as it sounds, this is a fairly high effort undertaking, and it requires domain expertise. Like if you don't know how to optimize queries, and this is going to be like fairly non-trivial for you to do. And then again, like this is only going to really help you if your queries are inefficient to begin with. Like if they're complex, if you have large data set sizes or high query volumes, this might not help you so much. You're going to have to like layer this with other approaches. Cool. So the next one I'm going to talk about is database read replicas. These are like exactly what they sound like. So you have essentially a read-only copy of your primary database that lags behind it somewhat in updates. And the reason for that is because you're sending all of your writes to the primary database, which then has to like confirm them and essentially forward along the writes to all of the read replicas. So there's like a little bit of a time delay before they see the write and also change their internal state to reflect it. The benefits of read replicas is that you can effectively load balance requests across them and the primary database to get much higher scaling limits in terms of like read throughput, right? Because now rather than just having your one database, you have multiple, and you can send like, for example, like 50% of your traffic to one, 50% of your traffic to the other, and therefore get like twice the throughput. You could also put them in different regions. So if you're like, for example, a US-based company, but you have a lot of users in Cape Town, well, there's like a lot of distance between you, like the users in Cape Town and potentially like the database that's potentially within the US. And so even if like the database like return query results instantaneously, they'd still have to travel over like the entire Atlantic Ocean, which could take a while. So by nature of putting them in different regions, you can get them closer to your users, which helps a lot. On the downside, however, like if your queries are inefficient, if they're complex, or if you have large data sets, like any individual query still potentially might take a long time to run. So even though you're able to scale up throughput, this is also sometimes not like a standalone solution that will get you to where you need to go. And moreover, they're fairly expensive because now instead of paying for one potentially expensive database, you have multiple, and they tend to be a lot harder to operate as well. Cool. So now we're going to do a little deep dive into caching, which is the last approach I'm going to talk about here. So the idea of caching is that you essentially, for any like computation that's expensive, you can compute it once, save the result set, and then store it in memory so that you can later access it again very, very quickly. And if you generally didn't have like writes to your database, this approach would be wonderful because it doesn't really matter how inefficient your queries are. It doesn't matter how many of them you have. Really, it doesn't matter if they're like complex and so forth. Like you will get really fast access because you're just taking the result, storing it in memory, and then you're just reading it out again. And this is like an O of 1 lookup into like an in-memory lock-free data structure. So you can't really get better than that. And that helps a lot with throughput as well. However, because like presumably like in the background, the state of your database is continuously changing, it's very likely that the state that you pre-computed and stored in your cache is going to go out of sync fairly quickly. And so you have to essentially decide like how you're going to maintain the state of the cache in a way that is acceptable given the semantics of your application. And that brings us back to this quote, right? So there are hypothetically two hard things in computer science, cache invalidation and naming things. Like cache invalidation is fairly notorious for being a lot more complicated than it might seem at the surface level. And there are fundamentally two different questions that you have to answer on pretty much a per query basis. The first is, when do you invalidate? And the second is, what do you invalidate? And there's kind of a spectrum of what can happen if you skew to a little bit on the too much invalidation side versus the not enough invalidation side, and I'll talk about that a little bit here. Right, so let's say that you have a tendency to aggressively evict and invalidate from your cache. That's going to lead to fairly slow reads, because presumably the reason you went with the cache at all is because the queries take quite a bit to run when they're not being cached, if you're just running them against your database. And so if they're not present in the cache, that means that you're going to be just sending those requests to your database. You're kind of back to square one. The reads are slow. And then moreover, let's say that you had fully anticipated that the vast majority of your queries are going to be resolved purely in the cache. If that is not the case unintentionally, then all of that traffic is going to go to your database instead, but maybe you didn't provision it with that in mind. Maybe you're like, oh, well, I'm going to be offloading all this traffic to the cache, so I'll go with a tiny EC2 instance for my database, and that'll be a-okay. But if that assumption turns out to be not true, then suddenly your database is falling over, you have a failure/outage, and that's not great, right? And then similarly, on the other side of the spectrum, if you don't invalidate enough, then the data in your cache could be really stale. Maybe these are values from 2 hours ago or something, and then your application is expecting fresh data, and it doesn't have that, and so it might act in kind of wonky ways that confuse your users. And then moreover, you also are just storing more things in memory, which tends to be fairly expensive. So in addition to having that heavy memory footprint, you're paying a lot more money for it. There have been startups that I've talked to that spend literally over $1 million a year on Redis, which is a lot of money for a startup. So this can kind of blow out of control pretty quickly. And then generally, the more writes that you have happening in the background, the more likely it is that you'll have to evict for your application to act in a normal way. And again, this leads to slow reads, more load on your primary database. And it's really common to add bugs to this that will outside of whether or not you get your eviction policy right, that will lead to failures and outages. And moreover, when you introduce a cache, you're transitioning from a realm where everything is nice and normal, and you're storing all of your data in your database, and you can use SQL, and you can use all of the nice ecosystem of tools around your database, to a realm where you suddenly just have this random key value store that you have to reconcile with your database, and all of that logic is encoded at the application layer. So you went from having a purely clean business logic type application to suddenly your application is filled with cache maintenance code, and that is a little bit unfortunate as well, because it's tech debt at the end of the day. So those are the three approaches that I'm talking about today, at least: query optimization, read replicas, caching. In practice, I wanted to point out that it's very likely that you will eventually use all of these techniques, because I mentioned previously, the specific cause of the problem tends to evolve over time, and if you're around for long enough, then these will all come into play. In fact, one common pattern that I see is, for example, running read replicas in different regions, but then they're not fast enough, and so you add a Redis cluster in front of those, and then on the side you have an entire team of people that have the domain expertise to optimize queries that are kind of tackling that in an ad hoc way as they arise over time. So it tends to be fairly complex overall. Cool. So now I'm going to transition into telling you more about ReadySet, and specifically how we aim to alleviate a lot of the pain points around caching. So we talked about caching, and there's a lot to like about it, right? You get really fast queries kind of regardless of other factors like query complexity, data set size, that sort of thing, since you're essentially putting when you're doing a read, you're just doing again this O of one lookup, but we talked about how they're not particularly ergonomic and they cause a lot of pain in other ways. And so ReadySet is focused on alleviating a lot of those specific pains. And so you can think of ReadySet as a cache that maintains itself and figures out how to do invalidations itself. So really what it's doing is keeping, you cache things in ReadySet, and then query results in ReadySet, and then it keeps the cached query results up to date in real time as the data in your database changes. So there's a little bit to unpack there, but the main impact of that is that you don't have to do any of this cache maintenance work yourself, because ReadySet behind the scenes is monitoring the tables in your database that you're caching from. It's seeing that, hey, there was some write that happened that changed the state in that table, and therefore that means that we have to refresh the cache downstream to reflect the update to that table. And it does this like all automatically by like essentially like receiving a replication stream from your primary database in the same way that a read replica would. So again, like the impact of this is you don't have to figure out cache maintenance yourself. And moreover, you shouldn't have to change your application to use this either, because we are wire compatible with MySQL and Postgres, which essentially just means that like to a database client library or ORM, your application, we just look like another database, and you can slot us in front of your existing database without changing any behaviors. We do support both like caching queries within ReadySet as well as proxying them back to your upstream database, as well as like fine-grained control over like what to cache versus not. So for example, you can send some traffic to ReadySet. You can be like, hey, like I'm profiling these queries, like these 3 are really slow, so let's cache those, but then like forget the rest because I don't want to spend the cost on memory to cache them. And so you can essentially just tell ReadySet like cache these, but not these, and the ones that aren't cached will just get sent to your primary database. And so it's a little bit more ergonomic that way. You could, of course, also treat us as more of a read replica because we're just giving you a connection string, and at a higher level of the stack, you can just say like, hey, like I'm gonna reroute some of my traffic to ReadySet instead of the primary database, so you have options. And then moreover, ReadySet helps you cache in multiple regions to get data closer to your end users, and it does this without a lot of the complexity that you typically associate with this.
Hey.
Do we know what that is?
Hey. One.
Wow. Is that better? Okay. Room's haunted, you guys. Like,
Someone's stuck in the speaker.
yeah, seriously. Cool. Cool. I'll just like dive back into this now. Yeah, so we try to do this caching in a pretty traffic-aware way. So essentially, like, let's say you have some users in London, and they are like issuing requests. Like, essentially, like the ReadySet like London node would only cache the data for those London users, and it kind of like does this all automatically. And I'll tell you a lot more about this in a later set of slides. So I'm going to just gloss over it for now because there's again a lot to unpack, and we'll build up to this. Cool. So I'm going to tell you all about ReadySet system internals, which I think are like the coolest part. But first, I wanted to like do like a really quick set of slides that gives you like the user experience of like how you interact with ReadySet, just to make it a little bit less abstract. So here we're just connecting to ReadySet. Like as I mentioned, we just give you a Postgres connection string, and so here I'm using like the pSQL client to connect to like the ReadySet host, and it's like the normal tool that you would use to do this, right?
2, 3, 4.
Then I'm going to issue a query against the IMDb dataset, which is what it sounds like. It's like a dataset of all the things on IMDb, and they just made it public. And it's doing a count, and it's doing a join. And I haven't optimized this at all. Like this is just like a fresh like Postgres Docker image, right? And so it's pretty slow off the bat, right? I haven't hand optimized anything. It takes like roughly 1.5 seconds to execute. So seeing that, we're like, that takes a pretty long time. Like let's try to cache this one. And so to enable caching, I'm going to run the same query, but I'm going to just prepend the statement, create cache from, and then do like the select statement from before. And that just like triggers the cache creation. So that's done. Cool. Now we're going to execute the same query again. And we can see this time it took like half a millisecond. So we went from 1.5 seconds to half a millisecond, and we just had to run like one statement. So that's kind of like what we're trying to do here. So now we're going to like take a look at how we do cache maintenance. So I'm going to issue just like a write that is intended to make the count be like 1 higher than it was previously. So we did the write, and now we're going to run the same query again, and we can see that the result is indeed 1 higher. So before it was 14145, now it's 14146, and it also took less than half a millisecond to complete. So I didn't have to do anything for that. It just figured it out itself because it was like, cool, like you changed the state in your database. We're going to update the cache state. Done, you know, so that's it. Cool. So now we're going to talk about how it works. Again, this is my favorite part, so it's most exciting. But I wanted to start off by just kind of like describing the main like idea and like the philosophy behind ReadySet, and that is that you can essentially enable automation around cache maintenance by like narrowing the scope of what you can cache, right? So let's say you have a general purpose caching system like Redis It's really wonderful because you can cache genuinely whatever you'd like in it. Like you can cache SQL query result sets, you can cache images, you can cache pre-rendered HTML, like the world's your oyster in that regard. But the trade-off that you're making there is that you have to DIY your cache maintenance, and you have to do like all of the things that we talked about previously in figuring out like how to do that. So the insight is like if we restrict the scope of what's cacheable to just SQL, which is a very common use case of Redis, then you can actually fully automate cache maintenance, having like made that trade-off. And so like the thought experiment behind ReadySet is essentially like, what if your cache had a query engine built in and like for all intents and purposes looked like a database, right? And so this is a little abstract, so bear with me. I'll like walk through an example, but essentially like what we're doing under the hood is we're creating, like whenever you cache something, we're creating a data flow graph in memory that represents that cached query. And then the nodes of the graph represent SQL operators that essentially compute those operators over incoming data, change their local state, and then forward the results along to like nodes below it in the graph. And then the root nodes are like the application base tables that you're caching from. Leaf nodes are the final cache query results, and then like all the nodes in between are just like intermediate state of your query. But I'll walk through an example so that makes more sense. The case study we're going to look at is Hacker News. So for those of you who aren't familiar, this is just like a really popular like tech forum type thing, and we're going to just look at like a toy query that might come out of like creating a page like this. So in this example, we're going to assume that there are two tables that we're going to be like caching from. The first is the stories table, and the second is the votes table. So the stories table is just storing like all the info about the Hacker News like forum posts. So there's like an ID column, an author, title, URL, etc. And then the votes table is just like a list of users as well as like the stories they voted for. So whenever a user votes for a story, we're just adding a row to that table. And the query we're going to look at is super simple. It's essentially just returning, like it's computing the vote count for a given story and then returning that alongside with the other story like content and metadata. And it's a prepared statement. Like note that like you probably can't see, but there's like a little question mark in the query. So it's like a parameterized query. Like when we actually execute a read, we're going to like give it a parameter, and it's going to return the vote count and story metadata for a given story ID that we ask it for. And so ReadySet is going to represent this query as a data flow graph. And recall I mentioned that the root nodes of the graph, so they're like in the little purple DB, blue DB, are the votes base table and the stories base table. Then below that, we have a node that's responsible for counting things that are coming from the votes base table. And then below that, we have one that's doing a join of like the count info with info from the stories base table. So it's like being like, cool, we've computed the vote count. I'm going to join that with the rest of the story info. And then we have like this little like reader leaf node on the bottom, and you can think of that as like the final cache, the one that like holds the final cached query results, and that's the only one that really matters to like end users. That's the one that we're going to be reading from. So now I'm going to walk through like what happens when we do both like a write and a read in ReadySet. So we'll start with writes. Like let's say a user comes along, in this case like Justin comes along and votes for story with ID 2. That is first going to be sent to the database. We have like a replication stream from the primary to ReadySet, so we're going to get that update, and then we're going to update the votes base table to like essentially insert that row. And so that's the first thing that happens. But then the votes base table is going to send this new row to the count node, which is the one below it in the graph. And then the count node is going to take that new input that Justin voted for story with ID 2, and it's going to increment the prior vote count for story with ID 2 by 1. So before it was 580, now it's 581. Then the count node is going to send this new vote count to the join node, which is the child node in the graph. And the join node is going to be like, cool, I received a new vote count for story 2. So now I'm going to change like the old result set of the join to have the new vote count, so it's up to date. And then finally, we're going to essentially like cache that, and then users are going to be able to access this new value. So then when we do a read, it's a lot less work. So remember, like this was a prepared statement, so there's a parameter we have to pass in. So let's say that the story that we're going to look up, do like a lookup for, has story ID 2. Essentially, like all we have to do to get the final like cache query result is go to this like reader/cache node and then do a lookup for parameter 2 on the ID column and return the row or like the set of rows that is associated with that input parameter. Cool. So now I'm going to talk about like the ready set, like what makes it interesting, like advanced concept type of thing. And it's called partial materialization, which you can think of as essentially just being a lazy query caching mechanism. So recall this, this graph from before. This is all being stored in memory. So when you look at this, you might be like, hey, like that's kind of a lot to store in memory, right? Like there's some base tables, there's some intermediate state, there's like the final cache state. And we talked about how memory is like fairly expensive. And so we're like, oh, maybe we don't want to store that many things in memory. And indeed, like one of ReadySet's like main goals is to avoid this memory overhead explosion. And our approach is as follows. Essentially, the graph will initially start off as empty. You can think of this as like the cache being cold. So you have to like do a cache warming type step. And then whenever we receive a new query that has like a new input parameter that we haven't seen before, we're going to lazily compute the result set for that query like as we receive it. And so it's going to be like somewhat slower the first time we run it, but then it'll be in the cache, and then it'll be like the cache will be warm, and then it'll be really fast in all subsequent retries. And then as like after we do that, like whenever like writes happen, like we're only going to really pay attention to the writes that have any impact on the specific result sets that we materialized so far. So if we like did a lookup, like a query that had like parameter 2 and one that had parameter 3, we're only going to care about writes that would impact the results of the query, like those two result sets rather than like any possible result set. And then eventually, like, let's say like, some time has gone on, we've seen a lot of like unique queries like with different parameters. Eventually, like, let's say we run out of memory because, that's life, we run out of memory sometimes. From there, like only then will we start evicting. And then you can choose like what caching policy you want for that. So we like, like you do like LRU, generational eviction, that sort of thing. We offer all the normal ones. And then say you want to go and like read that same query again, like one that you evicted, that would just bring us back to this like cold read situation. It'll be slightly slower the first time, then it'll be like in the cache for all subsequent lookups. And so by nature of doing this, we're able to save a lot on memory overhead. And I have like a visualization for this as well. So like this is the graph, like starting off as like entirely empty. Like a user comes around, does a request for story with ID 2. That gets sent to the reader/cache node. It's like, hey, like I don't have that. And so what it's gonna do is essentially recursively traverse up the data flow graph, asking each parent node if it has like the data that it needs to be able to like compute the result. And if it does, it'll send it down. If not, it'll just continue and ask its parent. And so in this case, like the reader node doesn't have it. So it's like, alrighty, I will ask the join node. And the join node's also empty because this is like the initialization, where we just initialized, like there's nothing in it yet. And so the join node is going to go ahead and ask the count node. Count node doesn't have it. Luckily, the base table nodes will necessarily have the data that you're looking for. And so in this case, the votes base table is going to be sending to the count node all of the votes for story ID 2. The count node is going to count those votes, and then it's going to send the results to the join node. The join node's going to be like, cool, I have the vote count. Let me ask the stories base table node for like the rest of the story metadata so I can compute the final query result. The stories base table will happily comply, send it back to the join node, and then it'll finally be cached in this like reader/cache node and return to the end user. So this is like a cold read in ReadySet, essentially. Cool. So now I'm going to circle back to the whole multi-region thing from before and talk about how you can take this like data flow idea and kind of extrapolate it to a scenario where you want to do caching in multiple regions. And internally, like within ReadySet, this is like we think of this essentially being a CDN for your database. And so before I do that, I wanted to just briefly talk about like what is a CDN in case not everyone is familiar. So a CDN tries to solve two problems. The first is this one of like data locality where, the example I used previously was like, let's say like you're a US-based company, you have a database in the US, but you have users elsewhere, like say Cape Town. Even if like your web server responded instantaneously, like the network times alone are going to be really expensive. And so like at the end of the day, page load times are going to be a little bit slow and maybe your users won't be happy. And so CDNs are intended to solve that problem. And they're also intended to solve the problem of like, a web server, like any given web server has like a finite amount of resources. And like, let's say, again, you're having like a big internet day and suddenly like everyone's looking at your site. Well, if we're surpassing this throughput threshold that we talked about before, then your web server might fall over and then none of the people that wanted to look at your site are going to see anything at all because there's an outage essentially. And so the idea of a CDN is like, rather than just having your one web server in one region, let's have multiple web servers in many different regions and then cache page results in those web servers close to end users. And so therefore you can both like load balance your requests across different web servers and then also have them be closer to end users. The problem with this approach, like nowadays, is like most websites are really dynamic, right? Like we're not just caching static content. Every time we like issue a request to a web server, the web server also has to like run a bunch of database queries. So it wouldn't really work to just like cache like full page results in the same way that it might if your websites were purely static. And so we have to think about like how can we like essentially also do this caching at the database level and provide a lot of these same benefits as normal CDNs. And so here is kind of like a graph, like a super abstract graph of what this might look like, and I'll like zoom in. But the idea is like you have a primary ready set cluster in the same region as your primary database. And so this would be like the whole like data flow graph that we talked about before. But then you're gonna essentially replicate just these like leaf nodes of the graph, like the reader nodes / cache nodes in different regions around the world. And so to make it a little bit simpler, like let's say we have these regions. So we have one in Canada, we have one on the West Coast, our primary one is on the East Coast, and then we have a node in London as well. And so what this would look like is, again, like the East Coast, like US cluster will have like the whole data flow graph, which is responsible for dealing with writes. And then all of the reader nodes are just gonna be responsible for like caching the final state for users in that region. And so like zooming in again, like, these are what some of the tables might look like. All of the reader nodes are going to have like disparate sets of data. Like they're not all going to be identical. It's going to be based on traffic from that region. And so I'll walk you through what a read would look like in this setting. So let's say we have a Canadian user and they issue a request that goes to the Canadian ready set node. Like the Canadian ready set node, unfortunately, does not have what that user is looking for. So it's going to send a request to the East Coast ready set node to like compute the result and send it back to it. And so the primary cluster will do that, send it back to the Canadian replica, and then the Canadian replica will return it to that user. This is like a cold read again, like life is good, the user has what they're looking for. And we'll just do another one for fun, like it's getting another record, cool. And now let's say that we have writes. So let's say somebody votes for story with ID 1. That write is gonna get sent to the primary database, which is in the same region as the primary ready set instance. And so the primary ready set instance is gonna like update its cache state to reflect that write. And then it's gonna send this new like updated cached value to only the regions that were previously storing that value rather than like all of them, because that would be like wasting work essentially. So like in this case, the California node and the London node both had a cache entry that had story with ID 1. And so the primary ready set instance is going to be sending the new updated cache value to that region. And so this is like the same concept as before of like, lazy like query caching, partial materialization, but kind of like expanded globally. Yeah. So yeah, that's pretty much it. I again wanted to highlight like caching isn't just for websites. Like it's really useful for websites, but it's useful in other contexts as well. Primarily, when you think about using caching, it's good for like read-heavy applications. That doesn't mean that you can't have writes at all, but like you want to do like more reads than writes typically. And then you also want to have like skewed access patterns. So like if you were never like rerunning the same query twice, you're not going to get like much of a benefit from caching because you're just like throwing away the result. You're never coming back to the cache entry. And so it's good if there's some like repetitiveness in the queries that you're issuing. Otherwise, caching in general just won't really be useful for you. And then also it's like presumably like you would only look at caching if you had like some latency and throughput requirements that you weren't already meeting. Like you wouldn't do it just for fun. Like presumably like there's some database read performance problem and you want to solve it. So you're going to invest in caching. And then finally, it's important that you have tolerance for eventual consistency because a cache is fundamentally like the system off to the side that's not part of your database, so it can't be like included in transactions. It's just storing some like slightly out of date state in ReadySet's case, and yeah. And I wanted to briefly talk about the historical context of this project. So this came out of a group at MIT. The paper, like if you're interested in the database, like internals aspect of it, then I'd highly recommend looking at this paper by Jenkset et al. From OSDI 2018. It's called Noria. It's like what we're based on. We're also on GitHub and we're open source, written in Rust. So if you want to check us out, QR code. Yeah, and then finally, I have to say we're hiring. So if you're interested, reach out. All of the open roles are on our jobs page. Yeah, thank you. How are we doing on time? Is there any time for questions? Yeah. Yeah. Oh.
I had a question. I was wondering why ReadySet wasn't in the right path and why there was the bin log replication. And then you took it to the next level to show, well, we'll just distribute ReadySet around the world. So that's the answer. But that's amazing. That's just spectacular. Yeah. Any questions? Okay. Yeah. Sorry.
Hey, do you guys have plans, or does it do now push-based notifications? Like, for example, on temporal semantics, like, in London at 12 o'clock, a whole bunch of queries are going to come in for this?
We get this feature request a lot. It's not on the roadmap like right now, but I imagine we'll get to it at some point.
I was wondering, how does your primary cache know like which replicas to push updates to? Like you said, it only pushes to the relevant ones and not all of them.
We just like store that information within it as well. I don't remember what data structure we use, but it is a data structure that stores all this info. It might just be a hash map.
Yeah. Pavel, you're up next. Former AWS engineer.
Gosh, that down. Thank you so much for that talk. It's fantastic to see somebody productionizing Noria. It sounds to me and to many other observers that Noria was the right approach, thinking about database caching via partial materialization. Do you believe that you've cracked the hardest problem in computer science? And part two, what have been the biggest challenges along the way?
Yeah, totally. So I come from like a very academic context. You're not allowed to make bold claims. So I feel like the answer, like, the CEO, like marketing answer is like, yeah, we totally cracked it. And then like the academic in me answer that's afraid of getting roasted is like, we may or may not help with this. In some cases, your mileage may vary. So, yeah, it depends on my mood. I'm kind of like, oscillating between the two right now. I think the hardest thing that we've seen is just like, we have to deal with like a lot of ORMs, and they're all kind of fickle in their own way, and sometimes they don't adhere to the binary protocol, and they all like generate queries in interesting ways. And like our goal is like making the developer experience really amazing, but the surface area of doing so is actually quite large. And so this has been an ongoing challenge, and that's why we're hiring. So if you want to help, yeah.
Cool. Thank you very much for that presentation. Just over here.
Yeah.
I'm curious. So this is obviously the storage layer. I'm also curious about the compute layer, right? Because if I just have all my EC2 instances in whatever data region in the US, I don't really get the benefits of this. I have to either be querying the database from a distributed place, so that either means like edge compute, or it means I have to go like global in my deployment mode, which is kind of not easy to start off with. So how do you see your tool working with, I guess, maybe smaller companies who want the benefits of this? In my case, I'm trying to serve customers in Kenya, and we spent like hours the other day looking at what's the fastest data center to get to customers in Kenya. The answer is there isn't any, and you're kind of stuffed until, I don't know, Google gets around to launching a data center over there. So
totally. So there's like two separate questions there, I feel. So the first one, really amazing question. I'm regretting not adding this to the deck. So I'm assuming that you're going to use like this like whole multi-region thing using like a serverless like application platform, e.g. Cloudflare Workers, Vercel, that sort of thing. With the second thing, like I don't know, like we're not gonna necessarily go like we're an AWS based. I don't think we're gonna like build out our own like points of presence or anything like that in the near future. So it kind of depends on like the extent to which we might partner with companies that do have more points of presence or that'd be the idea over time.
Thanks for the presentation. I was really excited for this talk, and it answered a lot of the questions as I was thinking, oh shit, what do you do here? And then you answered it, so I appreciated the flow. I'm more curious on like failed approaches you took, because I'm assuming you did some of the research initially, and I'm interested to see the failures that got you. I mean, one thing that came to mind when you showed this is Ben Johnson's like virtual file system stuff he's been doing with SQLite. It's really impressive, and also made me think there's probably some optimizations there. I'm just curious, why this approach? What were some other approaches, and were there any failures in those approaches going down that route?
Yeah, totally. And I think this is just like a fancy incremental view maintenance system at the end of the day. And there's like a lot of them like nowadays, and they all have different trade-offs. And I think it's like being fairly particular about like which trade-offs you select, right? Like we're not a strongly consistent system, and that means that we're not going to be the right choice for a large set of applications, but we're okay with that because it enables us to do like very well in this set of applications, and it also enables us to avoid this like memory overhead explosion issue, which I think is like by far the hardest thing to get right. And I think there's going to be like this whole like saga that we go through around just like query optimization, but it's not going to be like a normal database like Query Planner, because like it does not like look like you know what I mean? Like it's not a normal database, but we're trying to look like a database. But like so with a normal Query Planner, what you're trying to reduce is like computational like latencies at the end of the day, like how fast can you like execute a given SQL query. With this, like they will all be really fast assuming you spend a lot of memory on it, but like at some point that amount of memory might be impractical, so how can you reduce it? And like figuring out how to do this for all of SQL is hard, and I think a lot of like the challenges were there and like trying to get this to work with real applications.
So we can do 3 more questions, or 4.
Thanks, that was excellent. It made so much sense to me that I found myself asking, do you think that PostgreSQL will add this feature directly to the project?
Yeah, I think that there has been like an interesting history of like query caches in databases. Like I don't think Postgres ever had one built in, but I think MySQL deprecated theirs. And I think what Griffin's referring to is like they now have like a fancy like incremental view maintenance type thing, but I haven't played with it, so I couldn't tell you like what trade-offs it made. Yeah, I don't know. I'm not the Postgres team.
Yeah, understood.
So, yeah.
Interesting, thank you.
Thanks for the talk. One question I had was, do you ever like dynamically switch between storing stuff and computing stuff? Like kind of like a JIT engine or something like that?
It's kind of, there are certain queries that like, I was just talking about how some like are potentially not worth like caching all the things for. So you can like potentially just say for this type of query, you dynamically compute part of it and it might still be like cheaper. And so that's kind of like tying it all back to like the fun query optimization work that we're going to have to do and already have started to do in the fullness of time. But this is like a thing that you can play with.
Phil, over to you.
Sorry, not a question. And I hate to do the not a question thing, but an answer to Andrew's question, or potentially an answer. Postgres is not distributed, and this like a part of their offering is like globally you can ask queries about the closest to you. So Postgres on its own like can't do that. It's not that's why there are other products like Cockroach and Yugabyte that like try to offer a distributed service. But yeah, that's not what Postgres does right now.
Any more questions? Okay, well, thanks, Alana. It's so awesome that you could join us.
Thank you so much for having me. Yeah, it was really fun.
Yeah, I know you said you won't build out caching nodes around the world, but I hope you do. Like, ReadySet will just become insane.
Yeah, cool. Thank you, everyone.